Okay, so we're going to start with the lecture on the advanced lecture on principal components analysis for the 503 class. Let me switch over to PowerPoint here. Oh, right. Okay. Let me go back up to the beginning. Boom. Now, if I turn this over to slideshow, is this going to know what it's supposed to be doing? That's a good question, Michael. Okay, so we're going to start out with a review of statistics, then we're going to talk multivariate statistics, and then into PCA, which is the lab for this week. So what do we mean by multivariate data? Well, multivariate data just means that for a given object or instance or record, we have multiple variables, okay? So, you see this all the time in various large data sets. And in the case of images, what we're thinking about are using the individual bands of the image as individual variables and looking at how they covary. So if we have just one variable, then we have a univariate analysis. Here are some univariate frequency distributions showing, 3 different species in this case and their frequency along some environmental axis. And so this is just, again, individual and cumulative distributions of 3 species for 3 environmental variables. And you can see for each of the species, both the sort of central tendency of each species and the overlap between species. And when we're dealing with multiple variables, particularly in remote sensing, we often look at bivariate density surfaces. So here we've got 2 variables, variable 1 and variable 2, and their bivariate frequency. And this allows you to actually see in a better way how well, in this case, 3 species separate on these 2 axes. And that's something that might not occur on one axis, right? On one axis, you might have considerable overlap between, in this case, species tolerances for environmental conditions. But if you're looking at multiple variables, you might find pairs of variables where species are going to be separated in some combination of variables. And this becomes important for classification, by the way. As we'll see, where we have various land cover types and we're trying to separate them out on the basis of, in general, multiple bands of spectral information. And then we can have a trivariate probability distribution. This becomes more difficult to draw, certainly, but there's lots of programs that will do this kind of thing now. And so now we're looking at how individual species, or you could think of them as land cover types, are separated in more than 2 variables. So plotting this in 3 dimensions. Of course, once you get beyond 3 dimensions, it becomes very difficult to visualize what's going on. And one of the reasons why we'll see we use principal components analysis is that it helps us take higher order spaces. We refer to these, distributions in multiple dimensional, along multiple dimensions. We think of those multiple dimensions as a space, or we refer to them as a space. So visualizing high dimensional spaces where you might have 7 bands or 20 bands or more than that, principal components, as we'll see, allows you to reduce the dimensionality of those high dimensional spaces. So just briefly sort of thinking about exploratory data analysis in general, the first thing we generally want to do is graphical display, because we want to look at plausible models, because we want to assess the validity of model assumptions, because we want to look at outliers and assess normality. And this is going to be important, again, in classification. And it might suggest some kind of normalizing transformations. And generally, in one dimension, we use histograms to do that. When we start looking at multiple dimensions, we're generally thinking about scatter plots of variables and looking at whether or not we have heteroscedasticity. If you've done multivariate analysis, heteroscedasticity just means, is there a relationship between the variability of one variable and the variability of another variable? And, in the top case here, we can see that as the two variables plotted here increase, they become more variable. And so you get this sort of increasing variable as a function of the absolute value of each variable. So that's something we're looking for when we do principal components analysis. And, sometimes in remote sensing, we might look at something like a linearization transformation in order to make the data more regular and to get rid of this heteroscedasticity, and then also to detect outliers. And in general, what we're looking for when we have a bivariate plot, we're looking for an elliptical distribution of data, something you could fit an ellipsis to and more or less have points outside the ellipsis, or the ellipse, I should say, randomly distributed. And here I've just done a transformation to make that true. So, I have to look at something because no, I guess that's right. And as I said before, once you get past 3 dimensions, it's difficult to create graphs and other visualizations. Although in this case, we actually are displaying 4 dimensions in this graph because we're looking at 3 dimensions spatially and then plotting a 4th dimension of data using the size of those spheres that we're plotting in the 3-dimensional space. So with respect to graphing data, the first thing we're likely to do when we're doing an analysis of multivariate data is to look at a matrix of scatter plots. Okay, so looking at the values, pixel values in this case, it's another kind of data set, but in here, we're going to be looking at various bands of the images. And so with, I believe you can see this if I do this, yeah. So if we look at this graph right here, in the upper left, we have one variable listed here in the matrix of scatter plots that labels the x-axis and one variable that labels the y-axis. And so we can look at all the relationships between pairs of variables in a single group of plots. And then we can start to think about preliminary relationships among 3 or more variables, but it's difficult to assess just by looking at a large number of scatter plots how many sources of variability there are. So, you might look at all of these and say, well, yeah, I see high correlations actually between each of the variables being plotted and the others, but difficult to tell whether there's just a single pattern of covariability going on, or whether in fact there might be multiple sources of variability. So what are we doing when describing multiple variables? Well, in general, we're interested in the central tendency of a variable, right? So there's the formula for the univariate mean, and we're interested in dispersion, right? For one variable, the univariate variance. In describing multiple variables, we're also interested in association. So how does each variable relate to the remaining variables, and how are they related to one another? Sort of pairwise and then multi-pairwise relationships. Skip that. You should all be familiar, I hope, at this point with this kind of mathematical notation, which is what I use in general because it's so easy to take this and then convert into computer programs. Whoops. There we go. So if we're describing multiple variables, of course, the first thing we want to know is the mean of each variable. So at the top there on the right, we have the mean for a single variable, where I is that particular instance. I'm sorry, that's the vector of means of each of a series of variables from 1 to p. Okay, and then below that you can see we have a vector, so a single dimensional array, x bar, that gives us the means of each of the variables for all of the observations. And then for dispersion, with a single variable, we're thinking about variance or standard deviation. I'm not going to go through that because you should all know what variance is. But here's where things get different. We think about covariance now in terms of looking at multiple variables. And the covariance really is just mathematically the product of, so for two variables, x and y, the product of the residual between observation I, xi, minus the mean, so that's the residual, and the residual of the y variable for that same instance. So yi minus y bar, so that's the residual for y. And you sum those up for the two variables and over all the observations and divide by the number of observations minus 1. The interesting thing about this is that if you do this for the contribution of any given instance or observation that has both the x and the y variables associated with it, you either have a positive or a negative residual for each variable. And so you can kind of separate this out into a situation where we're showing, you could imagine plotting x versus y, where the mean x, you could normalize it so the mean x is 0 and the mean y is 0. And you could plot them in a space that shows whether or not you have a positive residual or a negative residual along the x-axis and the y-axis. And if you do that, what you find is that it gives you a way to understand how we come up with the notion of having a negative or a positive correlation or covariance between variables. So here we have, again, we've looked at two variables, one on the x-axis, one on the y-axis, and plotted their residual from their mean, so that that's, you know, 0. And so the little, you can imagine the little lines between the squares indicating whether or not the x variable is greater or less than 0, and the y-axis is indicating whether or not the whether or not the second variable is greater or less than 0. And if all those values wind up in the positive squares, what you wind up with is a positive correlation between the two. And when you sum up all the values, you're going to wind up with a positive value. And similarly, if you plot this out, if all the points wind up, or most of the points wind up in the negative part of that square, or the negative squares, then you're going to have a negative correlation. If those values wind up being sort of scattershot around, you know, around the origin there with equal number of points in both those negative and positive domains of the graph, then you're going to wind up with a low value, positive or negative. And it really doesn't matter. If the magnitude is small, then the sign becomes less important. You can have a small positive or a small negative correlation that doesn't really tell you very much about the data. And so if we look at all the variables in our in a data set, and again, this can be the bands in an image, we come up with a covariance table, okay, where each, you know, if you look, again, you should be able to see this little arrow, you know, where you have at the upper left-hand corner of the table, the covariance between, well, variable 1 in itself, which is just the variance of that variable. And then the covariance between, say, variable 2 and variable 1, or band 2 and band 1, and so on, until you've built out an entire table of the covariances between each band and every other band. So if you have 10 bands, you're going to have a 10 by 10 element array that holds those covariances. Okay, where if that covariance is greater than 0, you have a positively correlated variable, and depending on the magnitude of the variables, you know, the more of them that are located in that positive space, the larger the value you're going to have for variance. Okay. Conversely, if you have a negative correlation between the variables, the covariance is going to be less than 0. Okay. And then the variances along the diagonal, or the variances appear along the diagonal of the matrix. Okay. And it's a symmetric array that is, you know, you've got the correlation between, or covariance between, variable 1 and 2, and you've also got the covariance between 2 and 1, and those are the same values, because it doesn't matter which one comes first. We tend to use correlation coefficients to describe two variables, particularly in like a regression context. And correlation coefficients just make it easier to understand. Covariances are scaled by the absolute magnitude of the variables involved, whereas with correlation coefficients, as you can see in the upper right, what we do is we take the covariance and then we divide by the product of the two variances that are assigned to the two individual. So variable J, variable K, we look at the covariance between J and K divided by the product of the variances of J and K. And this allows us to have a value that scales between -1 and 1 and tells us whether or not, it tells us what fraction of the variability in both variables is explained by the covariance between them. So a high absolute value means a lot of variance is explained in a lot of the variance in the two variables is explained by their covariance. That is, there's not a lot of residual information in a particular pair of variables. And that gives you at the bottom just an idea of, graphically how much variance is being explained for various different values of R. And R is this variance over covariance over the product of the variances, but we use R squared that actually gets us to that interpretation as the fraction of the variance in the two variables. So for a collection of variables, we can generate a correlation matrix between each pair of variables taken one at a time to tell us how well correlated a particular, how high the correlations are between variables in a particular data set. And then finally, we have a univariate normal distribution that we're all familiar with. Similarly, we have the bivariate normal distribution, which is a function of both the mean values of each variable, the variances of the two variables, and then the covariances between the variables. And this gives you graphically an idea of what that looks like in terms of the two means, the two standard deviations, and then you can understand the correlation coefficient as that row there as a function of the ratio between the lengths of the major and the minor axes of an ellipse surrounding the point cloud of observations of each variable. And the greater the R value, that correlation coefficient, the more narrow and elongated the ellipse is going to be. I just put a summary in here to give you an idea about the notations used for describing both univariate and multivariate data. Okay, so now principal components analysis. First thing, it took me years to remember. Principal, PAL, is someone who holds a position or a rank, or and for instance, principal, PAL, means the head of a primary or secondary school. That's the principal. Principal is only a noun, and it refers to a basic truth, a law, an assumption, or rule. And actually, it turns out that although the words sound alike, they're distinct in origin, okay? And so they've always been different words in English, and we are interested in principal, PLE, components analysis. I'm sorry, principal, damn it. How did I do that? components analysis. So, gonna have to edit that out for sure. So principal components analysis is a statistical procedure that uses orthogonal transformation. What does orthogonal transformation means? It means we're going to do rotation of data around a set of axes in such a way that the axes remain at right angles to each other, okay? And that's what we refer to as principal components analysis, okay? And so PCA is going to condense the information contained in a large number of original variables into a smaller set of new composite variables, variables that are equal to the original variables times some weight. So like I was saying earlier, when you have a large number of variables, your scatter plot matrix may be too large to study and interpret. There would just be too many pairwise correlations between the variables to consider. So, you know, if you have 12 variables, there are going to be more than 200 three-dimensional, you know, taken three variables at a time, 200 three-dimensional scatter plots to be studied, and you can't keep that kind of stuff straight. So what we want to do is to reduce the number of variables from the original set to a few more interpretable linear combinations of the data, okay? And you'll sometimes hear PCA being talked about as a special case of factor analysis. And factor analysis is more general than PCA, and it can include things like non-orthogonal relationships between the transformed variables. So here's just a case of a data set I've gotten. You can see you've got 36 variables in there, and to study each one of them in each one of the scatter plots here in depth would be basically a nightmare. So when we have correlations between variables, which we also call multi-collinearity, so the data may more or less fall on a line or a plane in a lower number of dimensions, okay? So here we have two variables that have a very high correlation between them, okay? So this is temperature versus pressure. And so our observations fall out, in essence, most of the variability falls out along a single axis that we can call principal components 1, right? So going right through the center of that, that point cloud. And you can see the way I've drawn the arrows here, you know, it's sort of starting at a new imagined origin. So in fact, the lines would continue further, you know, forming a full X, but I've stopped them at a sort of imaginary origin point there. And that first principal component there, that PCA1, would explain most of the variability in the two variables. And then we would have some variability left over in the second principal component, which may or may not, which may be noise or may be related to some other factor that we're not displaying here. So here's a higher dimension example. So let's say we've taken tests that plot out, you know, that have scores for verbal, math, and logic tests. So we have 3 variables, but we would expect there'd be some correlation between those variables, okay? And so really, we probably have less than 2 dimensions, okay? So if they're all perfectly correlated, then we might only have 1 dimension. Of course, that isn't the way things work, but you would expect some level of correlation here, okay? And you can see here that what we've done is we've got three variables, x, y, and z, and you can fit a plane to, a geometric plane, to the data in such a way that you're actually explaining the three variables very well using two variables. I don't think it would be this good if you were actually looking at those test scores, but in this particular graphical case, that's the way it comes up. So what does it mean to do a principal components analysis? Well, let's start with two variables here. So let's say we're thinking about brightness variables in an image, okay? So individual bands, and we'll use bands and variables interchangeably because that's how we think about it. So I haven't plotted the data points here, okay, as I have in the lower right, because it would just be a mess. What I've done is simply plot an ellipse that encloses 95% of the observations that we're looking at, okay? And again, the extent to which that ellipse approximates a circle, that's going to represent low correlation between the two variables. To the extent that it's thinned out, the longer it gets relative to its width, the longer the major axis relative to the minor axis, the higher the correlation between the variables. And so we start with just the data points, imaginarily plotted within that ellipse, within a space formed by two variables, and then we have two mean values, U1 and U2, one for each of the variables. In the next step, we move the origin of the space, because what we want to do is we want to rotate around the center of mass of the distribution of points. And so that's the two means that we're interested in. So we're shifting the coordinate system so that, once again, we have the mean values being represented by the value 0. And then in that third step, we're rotating the set of coordinate axes so that they align with, in this case, because we only have two variables, the major axis of the ellipse, and because we're constraining this to be orthogonal, a second axis that is at a right angle to the first. And then if we imagine this red point being one of the original data points, we can now calculate new values for it that we refer to as the principal component values for all the points that made up the original data set, okay? But now, instead of having two, a pair of coordinates, one for x1 and one for x2, in variables that are correlated, what we have is a pair of coordinates in uncorrelated axes. And if you think about it, if you have, once you've done this rotation, you will have 0 correlation between your first principal component and your second principal component, because all the variability that was associated with the covariance between the first two variables is now reduced to 0, and the first principal component reflects the value, the magnitude of the values in those two variables for each point. So again, we have a vector X, and we have a variance covariance matrix. So we're going to think about a new set of variables, y, y1 through yp, where 1 through p represents both the number of original variables and the number of principal components we're going to get. And we're going to create these new variables or principal components by applying a weight to each one of the original variables. So each one of them in the lower right there, those little e's. E11 is the weight for principal component 1 that we apply to variable 1, and E12 is the weight for principal component 1 that we apply to the second variable, et cetera, et cetera. So you can kind of think of this as it's a linear equation, okay? And you can think of each one of those E1, 2 through P as coefficients of a linear equation. I should take out regression then. And then each new variable, yi, has a population variance and the covariance. And we can think about all the coefficients that go into creating that variable, yi, as in a vector. So for principal component I, we have EI, 1, 2, 3, 4, up to P, each one of them associated with one of the original variables. So how do we find the coefficients that give us our principal components? Well, it involves eigenvalues and eigenvectors of the covariance matrix. Okay, so we're going to use lambda 1 through lambda p equal the eigenvalues of the variance covariance matrix. Okay, these will be, okay, the new variances associated with our principal components. So lambda 1 is going to be the variance associated with the first principal component, et cetera, et cetera. And one of the nice things about principal components analysis is that the lambdas there are ordered in such a way that the first explains the most variance, and the second always explains less, and so on and so forth, until you get to your last eigenvalue, and that explains the least amount of variance. It explains what's left over, essentially. And then we're going to have a series of vectors, okay, 1 through P, okay, where each one of those denotes all of the coefficients that we're going to apply to get a particular principal component 1 through principal component P. Right. Variance for ith principal components is the ith eigenvalue. And we're going to select these E values, these weighting coefficients, such that the covariance between any principal component and all the other principal components is 0. Okay? How do you do this? You don't. Okay? There's an approach called the spectral decomposition theorem that goes in and actually calculates what your coefficient should be to satisfy these two constraints, these two main constraints, that each eigenvalue, the amount of variance being explained by a principal component, is less than the one before it, and that there's no covariance between principal components. And again, that's the orthogonality aspect of it. That's what those right angles mean. So, first principal component, linear combination of the x variables that has maximum variance, okay? And again, that's what it means when we're looking at 2 dimensions, to have the first principal component going through the long axis of that ellipse, because that means that that's where they're most highly correlated, okay? So we're not gonna select. The algorithm is gonna calculate what those coefficients should be, subject to the constraint that they're all equal to 1, or their value squared is equal to 1. For the second principal component, we're going to come up with a linear combination, right, using those coefficients, that accounts for as much of the remaining variation between variables as possible, as long as the correlation between the first and the second component is 0. And then all subsequent principal components will have the same property. They're going to be linear combinations that account for as much of the variance as remaining variance as possible, and they're not correlated with any of the other principal components. This is an important thing to keep in mind, which is that for instance, the second principal component explains as much variance as is left over after you've explained all the variance that you can with the first principal component. So it's as if you are looking at all the data after it has been normalized by that first variable. Okay, so each subsequent principal component has to be understood within the context of earlier principal components. I'm going to go through an example using a data set where two scientists looked at 329 communities around the country and rated them according to 9 criteria. And I've got those criteria there. Within that data set, except for housing and crime, the higher the score that they got on these variables, the better, okay? For housing and crime, the lower the score, the better, because a high housing score would be more expensive housing. A higher crime score means more crime. So for this particular data set, these variables are skewed, and so the scientists did a transformation to normalize the data. This is the first thing you'll get out of a principal components analysis. And again, it doesn't matter if it's housing, or images, you're going to get a set of eigenvalues. Okay, and so in this data set, there were 9 variables. Therefore, there are 9 components. Okay, and again, the eigenvalue is a variance value. Okay, so here we have eigenvalues that start with 0.3775, et cetera, et cetera. We can sum up the total variance associated with the data set to get a total 0.5225 there. And then we can go back and calculate the proportion of the variance that is associated with each one of the components. So that first eigenvalue is associated with 72% of the overall variance. So jumping back for a second, what does that tell us? That tells us there are actually strong correlations between the variables in our data set. And then we go to the next component, and that's, basically it's 0.0977, but that's basically a 0.1 or 10% of the variance associated with the second principal component. And then we'll always keep track of a cumulative value. So, the cumulative variance explained by the first principal component is 0.72. The cumulative variance being explained by the first and second is 0.82. And, it should be noted that although data sets of different types, of different sources, your judgment about which principal components are important, to have 72% of your variance being explained on that first principal component means, yeah, there's probably not a lot of important axes of variation, because you're left with whatever that is, 28% of variance left to be explained. That's like a quarter. So that's something that'll immediately pop out. That happens in images all the time. When you do principal components analysis on a Landsat image, generally 75 or 80% of the variance will pop out on that first axis. And then you have to look at all those other, the proportion of variance being explained in that context. So second component is 10%. Okay, well, 10%, that sounds like that's probably important. But as soon as you get below that, you're like, well, the third explains 5%, the fourth explains 4%, et cetera, et cetera. It's, the question will come up, which of these are actually important, okay? And I just did all that talking and it's all in the slide. So, except to say that, the first three principal components in this explain 87% of the variation. And that's a large percentage. And so in general, you might think, well, that's a good result for a PCA, because what you've done is you've started with 9 variables and you've said, 87% of the variability in those 9 variables is actually explained by 3 variables, which means that I really only need to interpret 3 variables in order to understand what's going on in my data set. This is the kind of plot you'll see very often when you're doing PCA. It's a scree plot, and what it shows is the cumulative, the component number on the x-axis, and then the eigenvalue on the y-axis, okay? And again, you can see that the eigenvalue for that first component is very large, and then it gets smaller and smaller. And so there's always some judgment that has to be shown about how many components you're actually interested in interpreting. So those are your eigenvalues. Now you have to compute principal component scores, okay? So the eigenvectors are the scores, right, for computing your new principal components from the original data. So you simply go through one by one and multiply each eigenvector, well, each element of the eigenvector by the associated variable to get a new score for an individual instance, an individual observation, or in our case with images, an individual pixel, okay? And you go through and do this for each one of the eigenvectors, okay? You can do a number of things to try to understand what your principal components mean. But the way I think is most straightforward is to actually calculate correlations between your original variables and your new principal components. So in this case, you've got 3 principal components there. You have the original variables, and what you find is that first principal component should always, it always represents the sort of the magnitude of the observations for all the variables. Okay, so in general, these are in images always positive. Okay, because the brightness of the pixels in each band are generally positively correlated. So this is sort of giving you a mean value for your observations. And if a particular variable doesn't relate very well to the overall mean, its correlation will be relatively small. Okay, so in this case, the first principal component, is highly correlated with the cost of housing, the availability of healthcare, the availability of transportation, arts opportunities in a town, and recreational opportunities in a town. Hey, this is Fort Collins, right? We have a high, if we were, I don't know if we're in this data set, but if we were, we would be, have a high score in principal component 1 because housing costs a lot. There is a lot of healthcare available in town. There's a reasonably good public transportation network. We have a lot of arts in the community and lots of recreational opportunities. And those things kind of co-vary. In this particular data set, principal components 2 is associated with lower values for the availability of health and more opportunities for recreation. And the third principal component is related to crime and recreation. So you can see recreation shows up on, in this case, on all 3 principal components, and it can, because there may be parts of the component, recreation is going to be due to probably the amount of property taxes, which is going to be related to housing. Part of it is going to be maybe related to the age distribution of people in a particular area, which means that, if they're younger, they might be doing more recreation, and maybe they have less need for access to healthcare. And then a third is, again, maybe places where you have a lot of recreational opportunities tend to be areas where there are a lot of kids get into trouble. So maybe there's a correlation there with crime. Remember that the second and third principal components don't explain a lot of variance, okay? So the magnitude of these correlations has to be is for computing each one of those principal components. It's the contribution to the principal components, but it's the eigenvalues that tell you the amount of variance being explained by those components. So there's some text here about each one of the components. I'm not going to go into that right now. One thing we often do is plot principal components against each other. So here we have principal component 1 and principal component 2 on the X and the Y axis. And we have each one of these represents a town, and the blue values represent extreme values for the the red values represent extreme values for the first principal component. So this would be, in order to get a high score, you would have high housing costs, high healthcare availability, high recreation, etc. So that red dot on the right is associated with all those conditions. And then conversely, the red dot on the left is a town where, housing costs are low, but so are the availability of healthcare and recreation and all that. And then those two blue dots are just there to show you the same sort of thing for the second principal component that's being plotted on the y-axis. So they would have either a high or a low degree of the variables that are associated with that second principal component. In principal components analysis, we can use either raw or standardized data. So standardized here just means, same thing it means anytime in statistics. That is, we can either take the raw values of the original variables and look at their correlation. Look at their covariances, or we can take each variable, subtract the mean, and divide by the standard deviation of that variable. And what that allows us to do is standardize or normalize the value so that each of the variables has the same mean, 0, because you've subtracted the mean, and the new standardized variables have both the same mean, 0, and the same standard deviation, 1. And so we do this in cases where the variables are, they might have, we might not want the absolute values of the variables to matter that much. That's when we use standardized data. So in remote sensing, we're generally dealing with one of two cases. Sometimes we're dealing with raw digital numbers, and those are scaled in kind of a sort of a case-by-case basis, right? And so we might want to use a standardization effect there. If we have radiances or reflectances, on the other hand, those reflect, absolute units that are the same for each variable, and therefore we could go with a raw PCA. And that's just giving you the formula for the standardization. Now, PCA uses, by default, the covariance matrix as sort of its input. That's what it's working on to get your eigenvalues and eigenvectors. You can also specify for PCA that it use a correlation matrix. And doing a PCA on a correlation matrix is equivalent to doing a PCA using standardized variables. So using raw data is equivalent to using a covariance matrix. Using a correlation matrix is the same as using, or equivalent to using, standardized variables. And you'll see it specified both ways. So important to know the distinction. They can either talk about standardized or unstandardized. They can also talk about covariance matrix or correlation matrix. And you will get different results depending on whether you're using raw data or standardized data. This is for that same data set with housing, and I'm not going to go into interpretations. You can go back and read this if you like. So PCA is a descriptive technique. It's not hypothesis testing. So your decisions with respect to, for instance, how many principal components you want to use have to be made on the basis of what provides a good, concise description of the data. Our decisions about what principal components to use, and we always use, if we use one, or if we use 3 principal components, it's always going to be like 1, 2, 3. You're not going to be like, well, we're going to use 1 and 2 1, 2, and 5, and we're going to ignore 3 and 4. But you're gonna think about it in terms of the importance of the variability being summarized to your problem, and not worry so much about significance levels, for instance. Again, some types of data sets tend to have more variability in common between variables than others. In remote sensing, we tend to have very high correlations between bands because ultimately, each band you can think of as the product of the brightness of illumination times the reflectance, of the materials in a particular pixel for that band. And so illumination is recorded in all of your visible near and mid-infrared bands. Becomes a little different when you get out into the thermal because you have some illumination effects, but you also have emittance effects. So in remote sensing, the first 3 principal components, for instance, of a Landsat image, you're generally talking about somewhere between 90 and 95% of variability, and anything above that is generally considered to be noise. And I'll just briefly say PCAs can also be used if you have a lot of variables to select explanatory variables for a regression. So, if you have a lot of variables that might be going into regression analysis, you might say, well, we have 4 or 5 variables here that are all highly correlated with a single component that's been computed, and we're not going to include all those variables. We're just going to select one to represent that effect. So one nice thing, as I said before, with principal components is it allows you to reduce the dimensionality, the number of bands in the data, and compresses much of the information in the original bands into fewer bands, okay? And these new bands are called components or principal components. And, again, if you think about TM, you might have 7 bands, that's 100% of the variance, and 3 principal components that explain 90%. And you might say, well, that's pretty much all the variability that we're interested in for this particular image. And it's not so common these days, but we used to use principal components analysis to reduce the number of bands in an image simply so that we could not have to store and process all the bands, because it was just easier to do 3 bands of processing instead of 7 bands. Not as important now because storage is cheap and processing power is abundant, but it is something to keep in mind. So I don't have as a slide the original image here, but this original image I present a number of times. It's our local scene, and you've looked at it in terms of both the original TM bands, and you've also looked at it, have you looked at it in terms of tassel cap? Well, here we have principal components, and where that first principal component in the upper left-hand corner, that image is going to be related to the mean values in each of the bands. And so that's basically just a brightness image, okay? So places that are highly vegetated appear dark because they generally have lower reflectance, right? So the forest areas appear dark, and the areas that are bright are areas with less vegetation, like rangeland areas and North Park. I should have gone through this. I hope you've seen this before. Here you have North Park up here, and then the Front Range, and bright areas where you have either bare soil or agriculture. Those tend to be bright areas. Here we have a second principal component. In general, with Landsat, second principal component is going to be related to vegetation, because if you have a scene that has vegetation in it, then again, the overall pattern is going to tend to be whether or not a particular pixel is bright or dark. The second most important pattern is going to be whether or not we see the contrast between red and near infrared that we expect when we have vegetation. And so in this case, you can see, I hope, that we've got a second image, a second principal component that's related to vegetation with, areas up in North Park and rangelands as having lower values, and agriculture and recreational grasses, i.e. people's front lawns, having high values in that second principal component. And remember that this is relative to that first principal component. So once we've taken out the effect of average brightness, what do we have left? Well, the biggest source of variability then is whether or not we see this contrast between red and near infrared. And then a third principal component here, and that's going to be related to the presence of ice or water. These are effects in the mid-infrared that tend to show up in a third principal component. And again, in this particular case, it probably explains somewhere between 90 and 95% of the variance in the entire image. And then in the lower left, again, the nice thing is that we started with, 6 non-thermal bands. Now we've got, which to look at them all in combination would be take a lot of time. Here we just have a 3-band image that we can display all at once that shows us the 90 some odd percent of the variability in the image, which is, very often all that we're interested in. And then the lower right hand at the bottom and the absolute lower right, just looking at various other principal component bands. And here we have 2 images, neither one of which really shows a lot in terms of patterns that we don't already see in that first lower left-hand image. So chances are we're not going to need those other principal components for our analysis. So some reminders: PCA transformation, basically a rotation of the original axes to new orientations that are orthogonal to each other, and therefore there's little or no correlation between variables or bands, depending on how you want to think about it. That first principal component is going to explain the maximum amount of variance in, for instance, in that case, the 7-dimensional space defined by 7 thematic mapper bands. And the first 3 principal components commonly contain over 90% of the image information. And then a lot of what you have in the higher principal components is actually noise, either atmospheric noise or sensor noise, things that are just uncorrelated with the primary sources of variability in the image. So here's an example of 6 bands here, because we've omitted the thermal. So TMs 1, 2, 3, 4, 5, and 7, and then 6 principal components for that. And what you see is that first principal component is the one that has the most in common with each one of the bands of TM, right? That's sort of the average brightness pattern. That is, we think of it as a redundancy in the bands. The bands contain similar information that's just related to the overall brightness of objects. And then we have a second principal component here that has a pattern that, I think you mostly see it in the mid-infrared. We can go back and look, we could go back and look at the coefficients for this, but very often with principal components on images, we're more interested in looking at the imagery. And then a third principal component here that again seems to have more to do with what's going on in the mid-infrared than, say, the first 4 bands. And then when we get out to the higher order principal components, you're seeing that there isn't much pattern, spatial pattern left to be explained. And you start seeing basically a lowering of contrast, and that's because, you know, mostly we have spatially uncorrelated sources of noise in those higher principal components that again might have to do with the atmosphere, might have to do with sensor biases, but that we're probably not interested in if we're interested in looking at the land surface. Principal components, here again, we have another TM image, 6 bands. You know, that first band is going to be brightness, and then you're going to have principal components to, in general, showing you the contrast between bands 3 and 4. Okay. And in this image, you know, bands 3, 4, 5, and 6 don't seem to be showing you very much at all. And here's a good example of another image that I think you've seen before, where that third principal component, you're seeing sensor errors there, okay? This is not something, I mean, some of this is down on the ground, but in the lower right-hand corner, you see that third principal component really showing up things that look like lag effects for a cross-track scanner, where it might hit a particularly bright pixel and then not there's a memory effect with the scanner where it's not recording as high a value for the next, you know, subsequent milliseconds, which, you know, is associated with the next few pixels being recorded. Again, here we have that principal component 1, 2, 3 image for the local scene, and in this case, 88% of variance is associated with the first principal component, and then 6 and 4 associated with the second and third component. And actually, you know, that's 99% of the variance being explained. So unlikely to see a lot of information that we're interested in being in principal components 4, 5, and 6. I should note that when you display principal components, as I have here, generally principal component 1 is associated with red, principal component 2 is associated with green, and principal component 3 is associated with the blue color gun. And here are the eigenvectors, and we can use those in this case, in lieu of correlation coefficients, to explain the relationship between each principal component and the original 6 bands. Here we have positive values for each one of, each one of the weights that we're going to use to compute this first principal component from our 6 original bands, which is constrained principal components itself. In this second principal component, what you'll find is there's this very high value for band 4 and a smaller but probably significant value for band 6. But this is actually expressing the vegetation signal. Now you might think, well, why don't you see a negative correlation for principal component 2? I'm sorry, for principal component 2 with band 3, you only see this positive value for near infrared. Well, again, the answer is that when we're looking at a principal component, we need to interpret it in the context of the other prior principal components. So principal component 1 is taken out the average brightness of the pixel. And so the vegetation is no longer expressed as the contrast between 3 and 4. It's being expressed as just a high value associated with NIR. Again, very, very common. Principal component 3 is a contrast between mid-infrared and the visible. So that would be a contrast where you have a negative values for a particular set of bands, and then a positive for another one. So you're looking at a contrast between those variables. And then as you get up again into 4, 5, and 6, kind of high value here for the contrast between the 2 mid-infrared bands. And honestly, I'm not sure what that means. It could actually just have to do with their response to atmospheric moisture. And principal component 5, a negative correlation with, or a contrast between blue and red. Again, not sure what that means. I don't think it's really meaningful. And again, you have to look at these in terms of their, these 2 variables are important, band 3 and band 1 for in the calculation of principal component 5. But principal component 5, we know, doesn't explain very much variance. So this is not a very strong pattern in the context of the image itself. So that's something to keep in mind when you're interpreting principal components. So why use principal components? It decorrelates your spectral data. Multispectral band data images are highly correlated. Their bands are highly correlated because the spectral properties of surfaces tend to be correlated. Things that are bright and blue tend to be bright and red in general, because you're just looking at the amount of illumination that you're getting for that particular pixel. That's compounded by topography, north slope versus south slope. And then sensor bands, there just tend to be correlations between the brightness in the different parts of the spectra that are being measured. So decorrelation separates those into independent components and puts them in different bands. And then it compresses the variance. So you might start with many, many bands and be able to reduce that to a few. Why not use PCA? It's data dependent. So the coefficients change from scene to scene, which makes consistent interpretation of PCA images difficult. That is, you have to go through this process of looking at the correlations or the eigenvector values before you can actually have an idea of what each band means. And then you can go ahead and look at what the particular interpretations are for each one, and then put that together when you look at a multi-band image made up of your principal components. Spectral detail, especially in small areas, can be lost in those higher order principal components. Anything where you have contrasts that are very different, when you have things that are very different than most other pixels, they are not going to explain a lot of variance, and therefore that pattern, that signature, is going to be put into one of the higher order principal components, which might not contribute very much to the overall image. It's computationally expensive because you have to calculate the covariance matrix between each band and the other band, and then perform this spectral decomposition in order to get your eigenvalues and eigenvectors. I should say that the spectral decomposition theorem, they are not referring to spectral in a light context. They're looking at it in a matrix. It's a confusing use of terms. Where am I? That's a good question. I'm going to briefly talk about tassel cap image at the same time I talk about PCA. even though I think I probably talked about it in the undergraduate lectures. So this is a tassel cap transformation of that same, 34, 32 path row Landsat image at the front range. Tassel cap is a transformation that is in a sense similar to principal components, except that the coefficients that are used to transform the original image into the tassel capped image are preset. They're calculated in another way, and they remain the same no matter what image you're looking at. So the advantage of a tassel cap transformation is that you can always interpret images the same way, no matter where they come from. There are fixed values or weights that are associated with each band that are used to come up with up to, depending on whether or not the I'm sorry, let me try that again. Tassel cap you mostly see with Landsat and sometimes with MODIS. Early Landsat images, you basically have two tassel capped indices that come out. One of them is brightness, one of them is greenness. And that's from the multispectral scanner sensor because it does not have mid-infrared. With Landsat TM, thematic mapper, and the subsequent sensors in the Landsat series, and with MODIS, you have mid-infrared, and so a third index, wetness, is calculated. This table on the right here gives you a bunch of other tassel cap components, but nobody ever uses them, so you can just ignore them. It's either brightness and greenness or brightness, greenness, and wetness. And the original use of tassel cap was in an agricultural setting, and what they were interested in is how individual crop pixels change throughout a season. So pixels start off here at the bottom of this little shape, and they, over the course of the season, they increase in greenness and they decrease in brightness. So here, increase in greenness, decrease in brightness. This is sort of the peak of the growing season. Then they get up to the point where they're ready for harvest, and that involves more increase in greenness, but also an increase in brightness. And that's because you tend to see more soil at that point, and because some of the spectral changes that occur within leaves. And then at the end of the growing season, pixels return to a state of being not very green and moderately bright. This was use of tassel cap was then extended to other conditions, and you can see that, in the same way a principal components makes things simpler by reducing the number of bands you're looking at, so does a tassel cap transformation. Essentially, you wind up having, if you're just looking at brightness and greenness, things down here at the tip of this shape are clear water because they're not very bright, and they're not very green. Turbid water is a little brighter because it's got like some soil in there and not very green. Concrete and urban spaces tend to be very bright and not very green. Whereas things like natural forest tend to be very green and not very bright because, of course, plants are absorbing light. So it simplifies the story that you have to tell about what's going on in an image and trying to figure out what individual pixels are doing. And here we just had some grayscale images. We have brightness, greenness, and wetness. These look very much like the first three principal components, of the same image. And that's for a good reason. I mean, brightness is basically the first principal component. Greenness, again, gives you the information about the contrast between bands 3 and 4, red, near infrared, and it tends to be the second most important source of variability in an image. And then wetness is a mid-infrared effect. And the one thing that TasselCap does nicely is that even though it's that third effect is called wetness, it in general, conifer forests tend to be to have higher wetness, even though they're not wet. It's just a function about how mid-infrared works in a conifer forest canopy. And so it can be used to separate out areas that are green, vegetated, like agriculture, or broadleaf forests, from areas that are green and in the conifer forest condition. And of course, we have a lot of conifer forests here in this scene. And then we have haze, again, an atmospheric effect, and then fifth and sixth, and I don't even know why they bothered calling them anything. And then here we have bands 1, 2, 3, and bands 4, 5, 6, again displayed as red, green, blue. And the one difference you see between TasselCap and components is that bands 4, 5, and 6, because they're not constrained to be uncorrelated with the earlier bands, you do see this overall pattern that shows up again in 4, 5, 6. That's really already been explained by 1, 2, 3. And again, 4, 5, 6 or haze 5, 6. Nobody uses these things. So, and as I was saying, there's if you look at the correlations between the principal components analysis of that, or principal components transforming that image, and the TasselCap, in general, you're looking at very similar patterns. I'm not going to go through this in detail, but whether it's principal components or brightness, greenness, wetness, you know, the correlations are conceptually similar. And here we have the actual scatter plot of principal component 1 versus TasselCap 1 for that image. You can see the first one is highly correlated. The second one, a little less. And then actually wetness, the third TasselCap, shows up much better in TasselCap than it does in the principal components analysis. So why do you use TasselCap? It's a fixed reference. Again, you can pick up an image from anywhere in the world and interpret it in terms of TasselCap. So you get this consistent interpretation, and the components are related to geophysical properties of the scene, whereas with principal components, it's just whatever is coming out in the data analysis. Why not use the TasselCap? Well, it's a non-optimal compression of the data. You don't get as much of the variance in the first 3 TasselCap indices as you do in the first 3 principal components. And if you don't have a set of TasselCap indices for a particular sensor, then creating them is kind of a hassle. To create the weights, essentially, that allow you to create a TasselCap. But again, I think for Sentinel, Landsat series, and for MODIS, which are kind of the big 3, those are components, or these indices, or the coefficients that make up the indices are available. Okay. Wow. That took longer than I'd hoped. But hopefully that will make your principal components lab more easy to do. And if you didn't know about principal components before, you sure as heck do now. And I'm going to shut off recording so you don't have to worry about being recorded. There we go. Do you want to stop cloud recording?